Hello students, in this video we will learn curve sketching using calculus. I think of this topic the same way how would an artist think painting a masterpiece. When I'm presented with a function to graph, I first identify the type of function I have, collect necessary data, use my data, and graph my masterpiece, which is the graph of my function. In this video, we will learn how to graph cubic functions using calculus. A general form of a cubic function, f of x, is of the form ax cubed plus bx squared plus cx plus d. A basic form of a cubic function is of the form f of x equals to ax cubed. Depending on the sign of the leading coefficient a, we may have one of the graphs showing on our screen. Also, the domain of a cubic function is all real numbers. So let's start with an example and graph our masterpiece. This is the cubic function we want to graph. F of x is equal to x cubed minus 3x plus 2. We will do so by using the steps shown on our screen to graph a polynomial function using calculus that I collected from our book. We will compute the first 3 steps, use the steps, and graph our function. Let's start with step 1. Step 1 says, compute the critical points of the function. To find the critical points, we will first compute the critical numbers. Anytime we're asked to find critical numbers, we know that we have to compute the first derivative of the function. In our case, we will find f prime of x. So, computing f prime of x, we apply the power rule for derivatives and have 3x squared minus 3. 2 is a constant. The derivative of a constant is 0, so we are done. Now, where does the critical numbers happen? Critical numbers happen when f prime of x is 0 or undefined. In our case, in our example, we have a polynomial, and polynomial is never undefined. So we will only consider the case of f prime of x equals to 0. So f prime of x is equal to 0. We will copy the value of f prime of x, 3x squared minus 3, under f prime of x. Bring down the equal and the 0. Now we have to solve for x. I will factor out a 3 and end up with x squared minus 1 equals to 0. Now this equation is true only if x squared minus 1 is equal to 0. Adding 1 to both sides, applying the square roots to both sides, we will have x is equal to plus and minus 1. Now we found our critical numbers. I will label my values with critical number and box these values so I can refer to them later. Now, are we done with step 1? We're not done. We're asked to find the critical points. We have the x value of our critical points. We want the y values of the critical points. To find the y values, we will evaluate the original function and at each x value of plus and minus 1. So if we let x equals to negative 1 in f of x, we will have negative 1 cubed minus 3 times negative 1 plus 2. And that should give me 4. Now for x equals to negative 1, we found y to be 4, and this is our critical point. I will just copy the critical point right here and label it as critical point. Box my answer because I want to use that later. Now evaluating f at 1, we will have 1 cubed minus 3 times 1 plus 2. And this should give me a 0. So when x is 1, y is 0, and this is my second critical point. I will copy it here, label my point with a critical point, box my answer, and keep it for later. Remember, I'm collecting data, so at the end I can graph my function. So I'm done with step 1. I wrote the data we collected from step 1 on the side, the critical numbers and points, so we may refer to them later. Moving to step 2. Step 2 says to use any of the derivative tests to find all local extremes. We know if there are local extremes, they will happen at the critical points. To find local extremes, we may apply the first derivative test or the second derivative test. In this video, I will show you how to apply both tests to find local extremes. As long as you apply the tests correctly, you will arrive to the same conclusion, meaning you will find the same result for local extremes. Let's start and apply the first derivative test. First derivative test. Now to apply the first derivative test, we have to find the sign of f prime of x around the critical numbers. We know that f prime of x is the slope of the tangent line to our graph f of x. We will do so by first graphing the number line. So I will start by graphing the number line. Then label my critical numbers -1 and 1. So I'm labeling -1 and 1 on my number line. Notice my critical numbers -1 and 1 has divided my number line into 3 intervals: -infinity, -1, -1, 1, and 1 infinity. I also like to label my number line with the function f prime of x to remind myself that when I find the values on each interval, I'm going to evaluate f prime of x at these values and decide on which interval my slope is positive and on which interval my slope is negative. I will start by considering the interval -infinity, -1. So -infinity, -1. I will choose random value on this interval and evaluate my f prime of x at that value. So if I choose -2 on this interval, if I let x equals to -2, my f prime of -2, so I'm evaluating at this function, my f prime of -2 will be 3 -2 squared minus 3. And this should give me a 9, and 9 is positive. What I would do is I will label the interval I evaluated in with a positive sign to tell myself not only at x equals to -2 in this interval, I will have a positive slope when I evaluate in f prime of x, but at any value I choose in this interval, I evaluate the value at f prime of x, I will have a positive slope. Now I will consider the interval -1 to 1, -1 to 1. If I let x equals to 0 in that interval, then I will have f prime of 0 equals to 3 times 0 squared minus 3, and that should give me a -3, which is less than 0. So I will label this interval -1 to 1 with a negative sign, again to remind myself that any value in this interval evaluated in f prime of x will give me a negative slope. Now I will consider the last interval, 1 to infinity. If I let x be 2 in this interval, then f prime of 2 is going to be 3 times 2 squared minus 3, and that should give me a 9, and 9 is positive. Again, I will mark this interval 1 to infinity with a positive sign, telling myself that the slope is positive here for any value of I choose in this interval. Now, the first derivative tests tell me if my sign changes from positive to negative, over a critical number, that means the critical point, in this case negative 1, 4, is a local maximum. So I would write a local max next to this point. So I know when I'm graphing that this point is going to be a local max. My first derivative test again tells me that if my sign changes from negative to positive over a critical number, in this case 1, then my point 1, 0 is a local minimum. So I will label my point with a local min. So this is the result I get from applying the first derivative test about my local extremes. Now, what else I can get from the data that I have here? I know that on this interval negative infinity, negative 1, I have a positive slope, and the same on the interval 1 to infinity. That tells me that my original function f of x is going to be increasing on these two intervals. Also, on the interval negative 1 and 1, the slope is negative. That means my original function will be decreasing on this interval. So now let's move and try the second derivative test to find local extremes. I added the data I collected from the previous step to the side, and now I will apply the second derivative test. To apply the second derivative test, I have to find f double prime of x. So f double prime of x, I have to apply the first derivative to 3x squared minus 3. Using the power rule again of derivatives, I will have 6x. I will now evaluate f double prime at each critical number. So I will start by evaluating f double prime at negative 1. And if I let x to be negative 1, I will have negative 6. The second derivative says if f double prime is negative, then my original function f of x is concave down, and I have a local maximum at that critical point, which in this case negative 1, 4. So I have a local maximum at the critical point negative 1, 4, and this is consistent with my finding from my first derivative test. Now I have to evaluate f double prime of 1. If I let x equals to 1, then I will have a positive 6. And my second derivative test says if the f double prime of the critical number is positive, then my original function f of x is concave up, and I have a local min at that point, at that critical point, which is 1, 0. So I have a local min at that point, which matches also my finding when I applied the first derivative test. So feel free to use any of the tests. As long as you apply them correct, you will arrive to the same conclusion as we saw. We now arrive to step 3, and step 3 says to evaluate random x values to locate more points. We did find the two most important points on our graph, the local max and min, but we still have to evaluate few more points to have a better sketch of our function. One particular point interested me is the inflection point, because by applying the second derivative test, the concavity changed between the local extremes, so I know there will be an inflection point between the two local extremes. To find the inflection point is we set f double prime of x equals to 0, find x, evaluate our original function f at the value of x we found. So we set f double prime of x equals to 0. We have the value of f double prime to be 6x. We copy it and under f prime of x. We bring down the equal and the 0. this equation is true only if x is equal to 0. So we evaluate our original function at x equals to 0. So f of 0 will be 0 cubed minus 3 times 0 plus 2, and that should give me 2. So 0, 2 is a point of inflection, and I will box this point to use it when I graph. Now, a better point the best points to find are the points to the left of the local max and points to the right of the local min. If I let x equals -2 and evaluate my original function at -2, I will have -2 cubed minus 3 times -2 plus 2, and this should give me a 0. So -2, 0 is a second point that I found. Now if I find a point to the right of the local min, I can let x be 2, and evaluating f at 2, I will have 2 cubed minus 3 times 2 plus 2, and that should give me 4. Now the point 2, 4 is a third point. Now I have enough points to graph my function, and I'm done with part 3. We now arrive to the final step, step 4. And step 4 says, graph the polynomial function using your data from steps 1 to 3. Now these are the data we collected. We found points. We found the local max and min. We know that our original function will be increasing on -infinity, -1 on this interval, also increasing from 1 to infinity on this interval. F of x also is decreasing from -1 to 1. Also, at the local max, f of x is concave down. At the local min, f of x is concave up. What we will do is plot our point on the x and y coordinate plane, connect our points, and graph our masterpiece. Starting with point 0, 2, we will plot 0, 2 right here. -2, 0 is right there. 0.24 is somewhere here. The local max is at -1, 4. It's somewhere here. We know f of x is concave down at this point, so we can just concave around this point. The local min is at 1, 0. And we have f of x concaved up on this, so we can just concave up around this point. All what we have to do now is connect our function f of x. So on this interval, we know f of x is increasing. On this interval, f of x is decreasing. Again, f of x increases on this interval right here, and we label f of x. This is the graph of our function, f of x equal to x cubed minus 3x plus 2. I hope you found this video helpful. Thank you.